Welcome to the third course. First course we did the introduction, why electric vehicle, the various fundamental aspects of it. In course 2 we took a deep dive into first cells, then battery packs. In course 3 we take a deep dive into motors and controllers used for electric vehicles, and then chargers used for electric vehicles. This course will be again taught, the chargers part will be taught by me, and Professor Kannan will teach motors and controllers. A very quick overview, more detailed overview we will do when we start teaching the course 3. This is also 4-week course. It is somewhat independent. If you have not done course 2, you can still do course 3, but as I have pointed out, always desirable to do it in sequence. EV motors and controllers, fundamentals and design, will go back to vehicles, dynamics, understanding flow, power and efficiency, torque production, speed and back EMF, what is called DQ equivalent circuit, field oriented control. You will start getting into fairly complex control systems, 3-phase AC, thermal design, engineering consideration and future design. This is the first of the of section 4, should have been ideally numbered as chapter 6. The second part of this course is battery charging and swapping and infrastructure management. I will be teaching this. We will introduce electric vehicle chargers, we will introduce charging and swapping. We will introduce slow charging and fast charging. We will talk about, is there a standardization required, why and what. We will talk about on-board chargers versus public chargers versus bulk chargers. We will get into economics of public chargers in Indian context. If you buy and put a charger, can you make money out of it? We will talk about infrastructure management. These two parts, these two chapters, I should have numbered these chapters as 6 and 7 to be in the sequence. These will be the course 3. It will come after 8 weeks, it will be 9th to 12th week. Little bit on EV motors and controllers. As I told you, we will talk about vehicle dynamics, overview of different drive modes, deriving motor torque from different forces acting on a vehicle, torque speed and power speed curves. Part of that would have been done in chapter 1. We will quickly put that together. Understanding how flow applies to water, electric current, heat and magnetic field. It is the same equations. You have flowing water, a flowing electric current, a flowing heat and flowing magnetic field. You know, one of the things that will make motors and controllers complex as well as interesting is 3 of these flows: electric current flow, the heat flow and magnetic flow gets combined out here. And of course, we will talk about power and efficiency, electrical and mechanical equivalents of power, and then we will talk about regeneration and electrical to mechanical conversion. We will talk about torque production from a motor, force on a wire in magnetic field and torque in a loop, on a loop. We will talk about commutation, and then we will come up with permanent magnet synchronous motor architecture. We will do reluctance and calculation of reluctance torque and phase angle advanced. We will get into a little bit of electromagnetics, but remember that we are not presuming any background, a mechanical engineering student, electrical engineering, computer science student, any of them can take it. We will talk about speed and back EMF, very important, and understanding of Faraday's law you would have studied in your school, and dynamics of simple PMDC motor and mechanical electric speed. We will then try to transform the electric vehicle parameters in what is called DQ equivalent circuit, DQ frame and its importance. Equivalent circuit in DQ reference frames, defining current and voltage limits of an electric vehicle motor, analyzing speed torque curve and flux weakening. Please note that here things will get a little more complex, but it is all right. If you can understand overview, if you want to design motors, you need to get into detail. Then we will define 3-phase AC motors, discussion of peak versus RMS, line versus phase current, star connection, phasor representation, Clark and Park transforms, and finally field oriented control, importance of field oriented control, MTPA control and flux weakening control. Each of these we will get into details. We will continue with thermal designs of motors, building blocks of thermal designs, thermal circuits, heat flow, heat transfer coefficient, conduction, convection, evaluating heat, calculating the resistances, conduction and convections. Thermal circuit for estimating temperature profile, thermal design of a controller. We will then take into account engineering condition to determine steel losses in a motor and its significance at higher speeds, noise, magnets, ripple torque, and performance consideration and manufacturing guidelines. And finally, future frontiers of EV motors and controllers, adapting a motor design, impact of number of turns and stack lengths, the rare earth problem, synchronous reluctance motor, the next generation motors, and axial flux motors and 2-phase heat transfers. In the second part of course 3, we will talk about battery charging, swapping and infra management. Introduction to EV charger, architecture and interfaces, charger efficiency, protection, power factor and costs. We will introduce what is called onboard charger and off-board chargers. And we will introduce 2 options, slow charging and fast charging. Understanding slow and fast charging and impact of life on the battery. We will talk about battery size and charging speeds, heat generated during fast charge and battery's capability of doing fast charge, and finally grid readiness of EV battery. We will then introduce the concept of swapping. That I remember I talked about swapping. We will get into much more detail. Need for swapping basically avoids the high capital cost. Energy operators and business models. We will introduce the concept of lock smart battery, something which will enable the swappable battery not to be stolen. Need for standardization, charger parameters in off-board public chargers and need standardization. We will talk about CHAdeMO, the Japanese standard, CCS, the European standard, and AC01, DC001 standards. We will talk about onboard chargers, vehicle specific proprietary chargers, understanding CCCV modes. We will talk about public chargers, slow charging stations, fast charging stations and bulk charging stations, charging infrastructure, protocols and required standardization, an overview of standardization bodies, charger standards and charging protocols across the globe. And then we will end with doing the economics of public chargers in Indian context. Is it a business viable? Can you set up the chargers? And economics of AC chargers and DC chargers. We will also talk about battery charging, swapping, infra management, bulk charging and substation, understanding concerns, requirements and architectures, distributed and centralized architecture of battery swapping, overview of swapping standard and what is called LSVBCC protocol. We will end by doing management of chargers and vehicles, remote monitoring, introduction to operating management systems and central management system, using handheld device for logistics, swapping, etc. etc. We will briefly talk about pilot at IIT Madras and also talk about data analytics, using statistical ML and AI model based techniques for estimation of battery parameters, safety risks, charging optimization, driving vehicle behavior, etc. That is the end of course 3. We will do more detailed introduction when we come to course 3.